everyone, thank you so much for clicking onto the video. Today's learning objectives are to firstly look at isotopes as atoms of the same element with different numbers of neutrons and different masses, and then to look at atomic structure in terms of the numbers of protons, neutrons and electrons for atoms and ions, given the atomic number, mass number and any ionic charge. So now we're going to look at the evolution of atomic structure. So we need to know that knowledge and understanding of atomic structure has evolved over time. So firstly we have Dalton's model, and he said that all matter is made up of tiny particles which we call atoms, and he suggested that an atom was a tiny solid ball. And in his model, he said that atoms couldn't be broken down into anything simpler. So, cannot be And he also thought that all atoms of the same element were all identical to each other. And after Dalton's model was made, scientists used this model to make predictions. But sometimes the results of their experiments were a surprise, and they didn't fit with this existing model, so this model made by Dalton. And so scientists had to change this model slightly to explain any new evidence that they found. So first we have Thomson's plum pudding model, and this was the first development of Dalton's model. And the evidence which drove this model was the discovery of electrons. And we can write electrons as e to the minus because electrons are always negatively charged. And Thomson's plum pudding model was based on the fact that an atom was made up of tiny negatively charged electrons, which are dotted about a positively charged sphere, which is like a plum pudding. So when we have plum puddings, we have the cake, and then all of the plums are scattered about randomly within this sphere. So we have negative charges, we have negative electrons, dotted about a positive sphere. And Thomson also said that we could break atoms down into smaller parts. And the next development of the atomic model is Rutherford's model. And he found that if he fired some positively charged particles at gold foil, they bounced back when they were expected to pass straight through. And so he concluded that there must be a central positive nucleus where most of the mass of the atom is found. So we had firing of positive charges bounced back from an atom. So we had lots and lots of atoms in the gold foil, fired these positive charges. He expected them to go straight through, but they actually bounced back. And so he made the conclusion that we must have a central positive nucleus. Where most of the mass is. And then we have Bohr's model of the atom, and this is much closer to the current model that we have now. And what Bohr found was that in-depth work on Rutherford's model showed that it had limitations and that the electrons should just spiral in towards the positive nucleus. And so he concluded that electrons move in fixed orbits. And this is around the central nucleus. And then after Bohr, scientists then discovered that the nucleus was made up of two types of subatomic particles. So we had protons and neutrons. And as a result of these discoveries, we now know that atoms can be broken down into smaller particles, so protons, neutrons, and electrons. Atoms of an element have identical numbers of protons and electrons, but can have different numbers of neutrons. And atoms of different elements have different numbers of protons and electrons. So they found that nucleus is made up of protons, which are positively charged, and neutrons. And these atoms can be split up into smaller particles, and we call these subatomic particles, and they're protons, neutrons, and electrons. We also have that atoms of an element can have a different number of neutrons but they have to have the same number of protons and electrons. But atoms of different elements can have different numbers of protons and electrons. Now we're going to look a bit more into subatomic particles. So atoms are made up of three fundamental subatomic particles. And so we have protons, neutrons, and also electrons. And the protons and neutrons we've seen make up the nucleus, so make up the central part of the atom. And they are held together by a force called the strong nuclear force. And this is much stronger than the electrostatic forces of attraction that hold electrons and protons together in the atom. And so it overcomes the repulsion between the protons in the nucleus. And so that's how this strong nuclear force can hold all the protons together, because normally they would repel each other because they have the same charge. And another thing to know about the strong nuclear force is that it acts only over very short distances, so only within the nucleus. And then what we need to know about electrons is that they surround this nucleus and they're found in a series of levels, which we call orbitals or shells, and these get further and further away from the nucleus. And so looking at this example of a helium atom, here we have a proton, so it's a positively charged subatomic particle which is found in the nucleus. And then this green one here is a neutron because it's also found in the nucleus, but it doesn't have a charge. And the yellow one is our electron. Because it's in a shell or an orbital around this nucleus. And so now we also need to look at all their relative charges and masses. So we need to know their relative charges and also their relative masses. And so here we have the subatomic particle. And so first looking at a proton, its relative charge is +1 and its relative mass is 1. And then we have a neutron, and its relative charge is 0 and relative mass is also 1. And then we have an electron, which has a relative charge of -1 and then a relative mass which is much smaller than a proton and a neutron. It actually comes out to be 1 over about 1,840, so a lot smaller than the proton and the neutron. So you need to make sure that you know all of these relative charges and masses. Now we're going to have a look at mass number, atomic number, and isotopes. So these are three definitions that you really need to know. And the first is the atomic number. And we sometimes write this as Z. And this is just equal to the number of protons in the nucleus. And so the number of electrons in the atom is equal to the proton number. The proton number is also the atomic number. And so atoms are electrically neutral because we have the same number of positive charges and negative charges. And the number of electrons in the outer shell of an atom determines the chemical properties of an element and also what sort of element it is. And the atomic number defines the chemical identity of an element. And one really important thing to know is that all atoms of the same element have the same atomic number. So also because the number of electrons in the atom is equal to the proton number, when we look at the proton number, that means that we can see also that the number of electrons is the same. And then the second definition that we need to know is the mass number, and we sometimes call this A, and this is equal to the total number of nucleons. So what we do is we add up the total number of protons and the total number of neutrons, which are both in the nucleus, together. And it's the nucleons that are responsible for almost all of the mass of an atom because electrons weigh virtually nothing. So we saw that the relative masses of protons and neutrons were 1 and electrons were 1 over 1,840, which is significantly smaller. And then the last definition we'll need to know is the definition of an isotope, and that's an atom of an element which has the same number of protons but a different number of neutrons. So because it has the same number of protons, it also has the same number of electrons. And different isotopes of the same element react chemically in exactly the same way. And this is because they have the same electron configuration, because they have the same number of electrons. And atoms of different isotopes of the same element vary in mass number because we have that mass number is equal to the total number of nucleons, so protons plus neutrons. And because they have a different number of neutrons, all isotopes' mass numbers will be different. So for example, if we looked at a general element, so if we called this general element X, and what we would have would be, we would have A at the top and then Z at the bottom. So X is the element, and then we have A as the mass number, and then Z here as the atomic or the proton number. So this is how they're set out in periodic tables. So for example, if we actually looked at one of the elements in the periodic table, so for example, we looked at oxygen, and oxygen has a mass number of 16, and then an atomic number of 8. So now we can work out how many protons, neutrons, and electrons we have in this oxygen atom. So we know that the atomic number is equal to the number of protons. So for protons, this is equal to Z, which is equal to 8. And then for electrons, this is also equal to Z because the number of electrons is equal to the number of protons. And so this is also equal to 8. And then for the number of neutrons, we need to use the fact that the mass number is the total number of nucleons. So adding protons and neutrons together. And so that means the number of neutrons must be the mass number, which is A, and then minus Z. So it must be 16 minus 8, which is equal to 8. So we must have 8 of each of these subatomic particles in an atom of oxygen. And we'll also need to look at some ions. So for example, taking this oxygen, if we had an O2 minus ion, so oxygen likes to gain 2 electrons to form an O2 minus ion. And so, for example, if we had O2 minus and we still had this mass number 16 and the atomic number as 8, because these don't change when we add electrons. And so what we have is that protons stay the same. So we still have protons equal to the atomic number, which is equal to 8. But now the electrons, because they were the same as the number of protons, but now we have a -2 charge. So we have 2 more negative charges. That means we have 2 more electrons. So now it must be 8 plus 2. So now we have 10 electrons. And then the number of neutrons will also stay the same because we haven't altered the mass number in any way because electrons don't affect the mass number. And so we still have the mass number minus the atomic number, which still gives us 8 neutrons.